Hello students. To proceed ahead with the chemical properties of haloalkane and haloarene, the reactions and chemical properties are broadly classified into three parts, students. The first one is nucleophilic substitution, then comes the elimination reactions, and then comes the reaction with metals. But for now, let us concentrate only on the topic what you see right now, that is nucleophilic substitution reaction. So, in this type of reaction, a nucleophile, as you can see all of you over here, for simplicity, I have taken it as OH. This nucleophile reacts with the haloalkane. This haloalkane over here, students, and that is your what? Substrate. Having a partial positive charge on the carbon atom, and obviously this X, that is the halogen representation, will take both the electrons and leave when this nucleophile will attack this positively charged carbon atom. Right? You have already studied this. So, as the halogen leaves, it is known as the leaving group, and as the nucleophile is going to substitute with the carbon, it is known as the incoming group, students. Clear? So, this is the quick revision of the nucleophilic substitution reaction. Now, in detail, the mechanism of this nucleophilic substitution reaction, students, is divided into two parts. As you can see over here clearly, students, it is known as Sn1 and Sn2 reaction, students. Can you see over here clearly? Sn1 and Sn2, students. S stands for substitution, N stands for nucleophilic, and 1 stands for monomolecular. Similarly, S substitution, nucleophilic, and 2 stands for bimolecular. So, in this topic, you have two types of mechanisms to study, that is substitution nucleophilic monomolecular and substitution nucleophilic bimolecular. Okay? So, students, let us begin with the detailed study of one of the mechanisms what we have seen. So, let us begin with Sn2 mechanism. So, as you can see over here, students, what is it? Sn2. Substitution nucleophilic bimolecular. Correct? So the reaction is like this, what you can see over here on the screen, students. So let me begin. Over here, can you see this is my substrate? Okay, those of you don't know, over here in the carbon where all these bonds are meeting, this is the carbon. Okay, so this is the substrate. So CH3Br, right? So this is methyl bromide. The nucleophile, again for the simplicity, I have taken it OH. So this nucleophile is attacking this alkyl halide, that is your haloalkane, from the backside. Clear all of you? It's a very important point, students. Okay, the nucleophile over here is going to attack the substrate over here from backside. Okay, this backside attack of the nucleophile on the haloalkane is going to lead this into a transition state. Okay, what is this? Transition state. Now, why this is a transition state, students? Because as you can see, the incoming nucleophile is coming from the backside, but the leaving group, that is the halogen, is going from the front side. Okay, that is the bond making and the bond breaking is taking place simultaneously, is taking place together, and that is why this is known as a transition state. And then finally, after this transition state comes your product. So the product you have got is methanol. As you can see, CH3OH. Clear all of you? Now, if you see very carefully, students, I have written the product is with inverted configuration. Now, why inverted configuration, students? Because if you see over here on the reactant side, the bromine is on the right side, right? Can you see it very clearly? But when on the product side, when you come, the OH is on the left hand side, and that is why with respect to the original reactant, the position of OH is in the opposite order, the reverse order, or we can say it is in the inverted fashion. That is why it is inverted configuration. Clear? Okay, so I hope you got an idea what is this Sn2 mechanism. Clear all of you? So let me just look upon to the important features of this mechanism, students. Okay, so now what did I tell you? This nucleophile is going to attack the haloalkane from the backside, which is going to lead into a transition state, and this transition state is going to give us the product. Now as you can see, this is entire only one step thing, students. This entire procedure is completed in a single step. So the first important feature of Sn2 mechanism is that it is a single step reaction. What it is? A single step reaction. Now I know all of you might be thinking, if it is a single step reaction, then why this 2 is coming over here, right? Chalo, that is the second important feature, students. Okay, now let us see why this is substitution nucleophilic bimolecular. Students, as it is a single step reaction, but the rate of the reaction, that means the rate, that means how fast the reaction proceeds, depends upon two things, and that is why it is substitution nucleophilic bimolecular. The rate, that means the how fast the reaction will proceed, depends upon the concentration of the haloalkane and also the concentration of the nucleophile. जो अगर दोनों का concentration ज़्यादा होगा तो the reaction will proceed faster, and if the concentration of them will be lower, the reaction will proceed slow. As the reaction depends upon the concentration of both the nucleophile as well as the haloalkane, that is why this is substitution nucleophilic bimolecular. Clear? Don't worry, students, I have written this in a next video. You can take a screenshot from them. Right now, let us go on to the third feature. Okay, all the features will be given to you in return. Now over here, let us begin to analyze one of the crucial points what I have told you. Can you see this transition state, students? I told you over here in the transition state, when the nucleophile will attack the alkyl halide, that is the haloalkane, from the back side, it will lead to a transition state. And in this transition state, students, what did I tell you? Recall, I told you that the bond making and the bond breaking takes place simultaneously, right? That is why only it will lead to a product, or else it won't. So over here, if this nucleophile has to attack this haloalkane from the back side, don't you think this haloalkane will lead to a transition state where the carbon in the center over here will be having 5 group for a temporary period of time? See, 1, 2, 3, 4 and 5, right? Now if you think that these are hydrogens, then the attack is very simple. But when this carbon will be surrounded by bulky groups over here, the attack of nucleophile will not be that simple. Understanding? When this carbon is surrounded by the bulky groups, then this OH will face a steric hindrance. Due to this, the bond making will not be that easy, and that is why you should not choose the haloalkane which is bulky in nature in order to get your substitution nucleophilic bimolecular mechanism. So students, over here, this once again the Sn2 mechanism, I have written it in nutshell. See that over here, can you see the nucleophile which is giving a backside attack to the haloalkane, leading to a transition state where the bond making and the bond breaking takes place simultaneously, and then ultimately we get a product with inverted configuration. Correct? Now you remember we discussed 3 features. Out of them, 2 features I have written it over here. See, it is a single step mechanism. Okay, so everything, the attack leading to a transition state and then forming a product takes place in a single step. Okay, then the rate of reaction, that means how fast the reaction will proceed, depends upon 2 things, and that is why it is known as what? Substitution nucleophilic bimolecular mechanism. So the rate of reaction depends upon the concentration of this nucleophile as well as the concentration of this haloalkane. Can you see it over here? Rate of reaction is directly proportional to the concentration of the nucleophile and the concentration of haloalkane, and that is why this is substitution nucleophilic bimolecular mechanism. Okay, so first just take this notes and take a screenshot of it so you can write it properly. Okay, so it is a single step mechanism and the rate of reaction is directly proportional to nucleophile and haloalkane. So the rate depends on both concentration of nucleophile and haloalkane, and hence it is a second order or a bimolecular reaction. Clear? Alright, so let us talk about the third feature, what I told you. I told you that the nucleophile is going to attack the haloalkane from the backside, which is going to lead to a transition state. And in this transition state, the carbon over here, for a temporary period, for a very short period of time, it is going to surround by 5 groups. Can you see? Now, students think, अगर ये हाइड्रोजन के बदले और बल्कियर ग्रुप्स होते यहाँ पे, तो will this nucleophile be able to attack the haloalkane easily? Think, यहाँ पे हाइड्रोजन था तो ये बैक साइड अटैक बहुत इजी था, पर इमेजिन कि यहाँ पे CH3 और CH3 ग्रुप आ जाएं, बल्किनेस बढ़ जाए, तो क्या ये न्यूक्लियोफाइल इतना इजीली अटैक कर पाएगा इस हेलोअल्केन को? नो, it won't, and that is why the rate of reaction will get slower. जितना बल्किनेस यहाँ पे बढ़ेगा ट्रांजिशन स्टेट पे, उतना बॉन्ड मेकिंग अच्छे से नहीं हो पाएगा. And you know, the bond making and bond breaking takes place simultaneously. So if the bond making is only not fast, will the bond breaking be fast? No. And hence the rate of entire reaction will get slowed down. Okay. So to summarize this point, let me give you the return work. Okay. So you can take the screenshot of the return work. Can you see this point? In the red bullet point, all of you. See this? Sure, let us read. In this mechanism, the transition state formed in which 5 groups are present around the carbon atom, and therefore the presence of bulky substituents tend to cause steric hindrance and makes the reaction difficult to occur. Now here, greater the steric hindrance, student, this is an important line, greater the steric hindrance, slower the reaction rate, and therefore the order of reactivity of haloalkane in substitution nucleophilic bimolecular mechanism is primary greater than secondary greater than tertiary. A tert group is having maximum steric hindrance, students, so that is why it will offer much difficulty for the nucleophile to attack the haloalkane, and therefore the rate of reaction will be slower. Compare it to secondary and primary. Primary will give you fastest Sn2 mechanism, students, but tertiary will give you the slowest. Okay, clear? Alright, students. So let me get now on to the last feature of this reaction. Okay, so as you know, we have already seen in this mechanism that the nucleophile attacks on the haloalkane from the back side. It leads to a transition state, and that ultimately gives you a product with inverted configuration. So this inverted configuration is my last feature, students. As earlier also I explained you that if you see on the reactant, the bromine, the halogen that is on the right hand side of the substrate. When this OH is attacking from the back side, coming to the transition state and giving you the product, on the product side, can you see it very carefully that OH is on the opposite configuration with respect to the substrate. Br is on the right hand side, then OH is on the left hand side, and this inverted configuration product leads to a technical term. Students, be very careful, I am giving you the term Walden inversion. Don't worry, I have returned this, so you don't have to worry about it, but you just need to know that the reaction will proceed with Walden configuration or Walden inversion. Okay. Also, students, you need to note very carefully over here that the entire mechanism will be very easily or will be very favored under aprotic solvents. Aprotic solvents, okay. Now, what are aprotic solvents? Aprotic solvents, students, which do not give hydrogen on dissolving, are aprotic solvents. This point is really very necessary when for those who are preparing for competitive examinations. Clear, all of you? So the return work of this feature is over here, so please kindly note this work. Can you see this bullet point in red again, students? In Sn2 mechanism, the nucleophile attacks from backside and the leaving group, that is the halogen, leaves from the front side. So the bond making and the bond breaking takes place simultaneously. As a result, the mechanism is accompanied by inversion of configuration called Walden inversion. Which inversion? Walden inversion. W-A-L-D-E-N inversion. And the presence of non-polar, that is aprotic solvents, actually favors this mechanism. Clear? Alright. So now let us test ourselves. What did we learn? Okay. So these are the questions from board examination, students. You can read the question very clearly over here. So the question is, in the following pair of halogen compounds, which will undergo Sn2 mechanism, that is the reaction, faster? Okay. As you can see, there are three questions. In the first A, B and C. Let us talk about A, the first one. Can you see over here, students, the first one, the number of carbon atoms is remaining the same. Can you see that? 1, 2, 3, 4. 1, 2, 3 and 4. So, in the first question, students, you'll have to judge between iodine and chlorine. Okay. In the second question, students, again, there is one carbon atom which is greater, that is more. If you see over here, cyclohexane ring on both the sides, right? Over here you have CH2Cl and you have only Cl. And in the third question, students, you have CH3. I'm sorry, students, over here 3 is not written. Okay, so I'll write it down. CH3 thrice Cl and CH3Cl. Can you see it properly, clearly, all of you students? Okay, so CH3 thrice Cl and CH3Cl. Okay, so let us reveal the answers, student. The answer for the first one will be iodine is a better living group, students. Because of its bulkiness and the large size, student, it will be a better living group. It will leave faster compared to chlorine. So, mark it very important, students. So, iodine being bigger in size, it will leave faster and hence this will undergo Sn2 reaction faster. Again, the answers are written, students, so don't worry. Just let us discuss them first. Over here in the second one, this compound will form a primary halide and therefore it will undergo Sn1 reaction faster. And in the last one, it is very clear now. This is a tert group, that is a tertiary group, and this is a primary group. So primary alkyl halide will undergo Sn2 reaction faster. Clear? So just note down the answers, student. So this is the first answer, student. As iodine is a better living group because of its larger size, it will be released at a faster rate in presence of the incoming nucleophile. Okay, let us go for the second and third answers, student. Alright, so now let us test ourselves. What did we learn? Okay, so these are the questions from board examination, students. You can read the question very clearly over here. So the question is, in the following pair of halogen compounds, which will undergo Sn2 mechanism, that is the reaction, faster? Okay, as you can see, there are three questions. In the first A, B and C. Let us talk about A, the first one. Can you see over here, students, the first one, the number of carbon atoms is remaining the same. Can you see that? 1, 2, 3, 4. 1, 2, 3 and 4. So, in the first question, students, you'll have to judge between iodine and chlorine. Okay. In the second question, students, again, there is one carbon atom which is greater, that is more. If you see over here, cyclohexane ring on both the sides, right? Over here, you have CH2Cl and you have only Cl. And in the third question, students, you have CH3. I'm sorry, students, over here 3 is not written. Okay, so I'll write it down. CH3 thrice Cl and CH3Cl. Can you see it properly, clearly, all of you students? Okay, so CH3 thrice Cl and CH3Cl. Okay, so let us reveal the answers, student. The answer for the first one will be iodine is a better living group, students. because of its bulkiness and the large size, student, it will be a better leaving group. It will leave faster compared to chlorine. So mark it very important, students. So iodine being bigger in size, it will leave faster, and hence this will undergo Sn2 reaction faster. Again, the answers are returned, students, so don't worry, just let us discuss them first. Over here in the second one, this compound will form a primary halide, and therefore it will undergo Sn1 reaction faster. And in the last one, it is very clear now, this is a tert group, that is a tertiary group, and this is a primary group. So primary alkyl halide will undergo Sn2 reaction faster. Clear? So just note down the answers, student. So this is the first answer, student. As iodine is a better living group because of its larger size, it will be released at a faster rate in presence of the incoming nucleophile. Okay, let us go for the second and third answers, student. Alright, and these are the answers to the next questions, students. As you can see in the B part, the first option will give you a primary halide, and therefore it undergoes Sn2 reaction faster. And in the third one, it was really very clear between a tert and a primary group. A primary halide will undergo Sn2 reaction faster. And as you can see, we have Sn1 mechanism coming further. So keep up the spirits, and let's meet in the next video. Alright, so now let us begin with the second type of mechanism what we encounter, and that is your Sn1 mechanism. So can you see over here, substitution nucleophilic monomolecular mechanism. Students, the most important striking difference between Sn1 and Sn2 is right there front of your screen. Can you see that? If you remember, I told you that Sn2 is a single step mechanism, right? Everything occurs in entire one step. But here, Sn1 mechanism is a two-step mechanism, students. How many steps? Two steps. Okay, so now let us begin with the detailed study of this mechanism. As you can see, the first step over here is the heterolytic fission of haloalkane to generate carbocation intermediate. Over here, can you see it very carefully, students? The carbon, and these are the three groups attached to the carbon. This is your living group, and there is a heterolytic fission. The chlorine is taking away both the electrons of the bond pair and getting separated over here. It's coming over here, and because of that, what is being generated? A carbon with a partial positive charge, which is carbocation. As you can see very carefully, students, it is the chlorine taking away both the electrons. So this type of fission is known as what? Heterolytic fission. And I have also mentioned, students, very carefully, if you see, it is a slow step. Which step it is? Slow step. So in a mechanism, students, remember always any step which is slow, it governs the rate of mechanism. That means the rate of entire mechanism depends upon this step, and that is why the first step of this mechanism becomes your rate determining step, students. What it becomes? Rate determining step. Okay, so in the first step, because of the heterolytic fission, a carbocation intermediate is being generated. Let us move on to the second step of the mechanism, students. Can you see the second step over here? The second step over here is clearly shown, and that is the attack of nucleophile on the carbocation. Okay, so can you see this clearly? The attack of the nucleophile. Over here, again for the simplicity, students, I have taken OH. This nucleophile attacks the generated carbocation in two ways. It is attacking from the front side, and it is also attacking from the back side. Can you see over here? Front as well as the back side attack, and as a result of which there are two products which are being formed. Only the positions of the OH, students, in this products are changed. If you see in the main substrate over here, the chlorine is on the right hand side of the substrate. So in one of the products, OH is taking the right hand side, and in another one where is the backside attack, the OH is taking the left hand side. So where the OH is substituted originally as the position of the chlorine, students, that becomes retention of configuration, students. What it becomes? Retention of configuration. And where the OH is on the another side, the opposite side of the chlorine, then it becomes inversion of configuration. I hope inversion of configuration you remind of something which we have already seen in Sn2. Remember, so there are two products being formed, one with retention and another. Oh, hello students. I'm so sorry. In the last video, the last part became somewhat hazy and the last word was also missing. So I was on the point that one product will be forming with retention of configuration and another product will be forming with inversion of configuration. Okay, so now let us begin ahead with some of the important features of this mechanism. So as we did in Sn2, the similar way we'll do in Sn1. Okay, I'll be discussing them right now, and then in the next video you will get the return part of it, so you can take the screenshots. Okay, so let us begin. The first and the foremost important feature you're already seeing in front of you, students, that Sn1 mechanism is a two-step mechanism. Okay, step 1 was the hydrolytic fission, which was generating the carbocation, and the step 2 was the attack of the nucleophile on the carbocation. Okay, and this one, in this mechanism, the first step is a very slow step, students, right? And as I told you, the slow step gives you the entire rate of the reaction, so it is the rate determining step. Okay, the second most important feature, students, so now you can guess why this is known as Sn1 mechanism, students, because the rate of the overall both the steps depends only on one thing, and that is why this is substitution nucleophilic monomolecular. So the rate of the entire reaction, students, here depends only and only on the concentration of the haloalkane, that is the substrate. In contrast to Sn2, if you remember, it was a second order bimolecular reaction. Why? Because it was dependent upon the concentration of the nucleophile as well as the substrate. Over here in Sn1, it only and only depends upon the concentration of your substrate, that is your haloalkane, and that is why this is substitution nucleophilic monomolecular. Clear? Okay. Now quickly coming to your third and important feature again. If you see over here, students, while the hydrolytic fission, what is being generated? Carbocation as the intermediate. And as you know, intermediate is really very important for the formation of the product, student. So this intermediate should be as stable as possible, right or wrong? Because if the stability of this intermediate is not good enough, the products are not going to be formed quickly. And that is why the rate of the reaction also is dependent upon the stability of this carbocation, students. Now, definitely you have studied the stability of the carbocation, yes or no? Yeah, so we all know that a tertiary carbocation is very stable compared to secondary, and secondary is stable compared to primary. So your Sn1 mechanism, student, is going to be favored by tertiary haloalkanes followed by secondary and followed by primary. The tertiary haloalkane is going to react faster in Sn1 mechanism, students, and the primary is going to react slowly. Don't you think this is also the most striking contrast and a difference between Sn2 and Sn1? Okay. Hello. So these are the important features, students, which we discussed in the last video. So the first two is written in right in front of you on your screen. So can you read them? So the first one is, it's a two-step mechanism, student. Sn1 is a two-step mechanism, right? The first step in which is slow and is reversible, and hence it is also the rate determining step, student. It is the rate determining step, the RDS. Okay, and the rate of reaction over here is directly proportional to only one thing, students, that is the concentration of haloalkane, and so it becomes a first order that is unimolecular reaction, monomolecular that is. And the second step in compared to first is really very fast. Clear all of you? Now comes the third feature what we talked about in the last video, students. So over here it is. Yeah. So can you see that, students? The third point, in this mechanism, the carbocation is formed as an intermediate. So greater the stability of carbocation, students, the greater is the rate of formation of alcohol, that is your product. Okay. So the order of reactivity also depends upon the stability of carbocation, and thus the order of the reaction is something like this: tertiary greater than secondary greater than primary. Clear? And so it is highly opposite to that of Sn2. That is, in Sn2 you know that primary was reacting faster, but in Sn1 now you know that tertiary will react faster. There is also a note, student, if you see it very carefully, that the benzylic and allylic will also be discussed later. Okay. And another important point what you need to note over here, students, is coming. This is the point. The phenyl and vinyl carbocations are unstable, students. So they do not usually undergo Sn1 or Sn2 reactions. Clear? It's a very important point from MCQ and your assertion reason point of view, students. So please make it a note that phenyl and vinyl carbocations are unstable. They usually do not undergo Sn1 and Sn2 substitution, nucleophilic, monomolecular and bimolecular reactions. We have another chemical reactions for that which will be discussed later. Clear? Okay. So the last feature, students. For the last feature, let me make you recall to the second step of the mechanism again. Can you see the second step? The attack of the nucleophile on the carbocation. In this step, students, I told you that the nucleophile is about to attack the carbocation, which is the intermediate, by two sides. The front side as well as the back side, right? And as a result of which, there are two products which are being formed. The one with the retention of configuration and the other with the inversion of configuration. Student, the pair of the compounds which are being formed over here is known as a racemic pair. Okay, and the process is known as racemization. Clear? What it is known as? Racemization. The pair are also termed as enantiomers, student. Now, what are these enantiomers? Don't worry, we will do it in the next lesson, students, for the optical activity. But for time being, you need to remember that in the compounds where only the position of this nucleophile is different, that pair of compounds are termed as racemic pair, or they are also termed as enantiomers. There is one more term, students, which we will discover later on. And now I'll give you this point in return. Okay, so don't you worry, this point is there with me in return. Please make a note of it, and it's a very important point, students, if you see over here. Clear? So in the second step of mechanism, the nucleophile can attack from either side of carbocation, and so it results in the formation of mixture of enantiomers. Now you know, students, what are enantiomers, right? The one having the same configuration and the other having opposite configuration of the compound with respect to haloalkane. And so the mechanism is accompanied by racemization. Clear, all of you, students? Okay. Now let us begin with the questions. Okay. As we did in Sn2, students, the similar thing we'll do in Sn1 also. Okay, so now over here I have already given you the answers also. I'll just give you a method how to come to the answer. The question again remains the same, the drill is the same. In the following pairs of halogen compounds, you need to choose which one will undergo Sn1 reaction faster. Okay, so this is the first one and this is the second one. If you look carefully for the first one, this and this compound, just remove the halogen, students. Just try and remove the halogen. If you will remove the halogen over here, the carbon over here will become a tertiary carbon. And if you remove the halogen over here, students, the carbon over here will become a secondary. And you know that a tertiary carbocation is more stable. And more stable the intermediate in this mechanism, more faster is the reaction. So the first answer is that this compound will form a tertiary carbocation and hence it will undergo Sn1 reaction faster. So now can you choose between this and this, students? Very simple. Again the same drill. What you need to do, just remove the bromine over here from both the compounds. Over here, if you'll remove the bromine, the carbon will be a primary carbon, and if you here remove the bromine, the carbon will become a secondary carbon. So the second compound of the two will undergo faster Sn1 reaction. I hope it's clear, students.